Hi. Hi, can you hear us? Okay. Yeah. Hey, good afternoon all. I am Ravi and this is my colleague Jnanapriya. We are from Marvell and we are here. Initially we were slated to be between you and lunch, but Ashay graciously made it more difficult by making us be between your sleep and okay, but let's go ahead. Before getting the talk, a brief overview about Marvell. People long involved with SONiC will already know that Marvell has been involved with SI and SONiC for close to the very first product supporting SI and SONiC was launched by Marvell way back in 2017. There are companies like Xplant, KVM and later Innovium which are all part of the Marvell products which we are going to talk about. And a difference is Marvell believes in contributing all the features to SONiC community directly rather than having any private folks. And some of the so-called premium features we see like ARS, mirror on drop, all these features are being actively worked on Marvell to be contributed to the community. This talk is something continuing on the same lines where we want to add the Ultra Ethernet consortium features that have been discussed over the couple of days into SONiC. So we are going to talk about how we plan to integrate it into community SONiC available for all of us. And personally, I have been involved with SI and SONiC representing Marvell for more than 8 years, and this is the third year I am attending the SONiC India community, and it's really inspiring to see the community, India community especially growing stronger every year. And Ryan yesterday was talking about the SONiC Technical Steering Committee. I had been representing Marvell as a voting member in this Technical Steering Committee, and currently I am the only person from India in the Technical Steering Committee voting member, and I would like more people from India to also be part of the Technical Steering Committee. And if there are any, I will be all ears to get feedback or any suggestions from you that can be taken to the Technical Steering Committee to do anything that can make our India community grow even better. That said, we will get into the talk. Today we will walk you through what is scale-out network or why we need scale-out network. Many of us have been talking about it many times, and still there are some questions outside in the corridors, hallways. Hope we can clear up some of the doubts or maybe add more to the confusion. But we will again talk about scale-out, why scale-out, and what is the role of UEC in scale-out, and then how SI and SONiC, how we all fit into these things. Next, we will talk for need for link layer recovery. Yesterday Chintan covered some of it, and we will again do a recap or some deep dive into why we need link layer recovery. And then we talk about two of the link layer reliability features introduced in UEC 1.0 spec, which is link layer retry and CBFC. Last, we will conclude with the call to action, how the community can get involved, and we summarize the key takeaways from our talk. This is a visually challenging picture taken directly out of the UEC 1.0 spec. The system overview of the UEC 1.0 spec starts with this picture. Visually challenging, but this really brings out the amount of complex or tremendous work that has been done by the consortium the last relatively short amount of time. A lot of work has been done in the UEC 1.0 spec. Just before getting the picture, let us understand why we need scale-out network. Talked about many times, but same thing. Why we need scale-out networks? All the large language models, other things that we are seeing, needs to be trained across, if not tens of thousands of GPUs, hundreds to 150,000 of GPUs and stuff. GPT-6 is rumored, GPT-5 is speculated to be around 200,000 of GPUs and stuff. So these GPUs cannot be housed in a single rack, and yesterday we were talking about UA-Link, and in UA-Link spec, in one pod we can support up to 1024 GPUs. The large language models we are talking about span much across more than those number of GPUs, and therefore you need to have GPUs talking across racks, and like Chintan was saying, in some cases across data centers if there are power constraints on a given site. So, scale out network is what connects these GPUs across all these racks. And the next question is, what should be the technology for this scale out network? The industry has come together to make the UEC consortium, where they want to make Ethernet be ready and capable to do this scale out network. That is what UEC spec is doing, and there are a lot of areas that UEC is addressing. This picture, complex, but gives a brief of what all is being done. On the left, you see something like the node, which is all our servers housing the GPU servers. All the GPUs are inside these servers, which is called as a node. And then there are thousands and thousands of these nodes are connected through a fabric, which is composed of all the switches. This fabric is an Ethernet based fabric with regular switches. Now, if you deep dive into what a switch is, this picture also comes from the UEC spec, and this spec shows that what runs on the switch is something very close to what we know as SONiC. This is very close, this is not SONiC as such, but this is very close to what is SONiC. We see a SI layer. This is standard OCP SI, and we at UEC are working on creating the extensions in the existing OCP SI to configure the alternate features. And then in this talk, we are talking about how this is going to get integrated into our SONiC. Lastly, just a context on why we are talking all this. Marvell has been very actively involved in defining the UEC features in the UEC spec. We are working within the UEC SI working group to get the SI definitions being ready, and in this talk, Jnanapriya is going to talk about how this will be integrated into SONiC. Now going back, need for link layer reliability. Just deep dive on what Chintan covered yesterday. I'll slightly go off the slides. I had a couple of questions, interesting discussions, and a lot of questions of why is this really needed, etc. in the corridors. So slightly off before even starting here. Just drill down. We talked about scale out Ethernet networks. Thousands and thousands of GPUs connected via scale out Ethernet networks. And what are the applications of the workload that runs on the scale out Ethernet networks? These are the large language models we are talking about. GPT-5 that would have been on this, GPT-6, all this that are going to come up are all running on this large number of GPUs connected via this scale out networks. Now, these training jobs where the LLMs are getting trained are called as distributed training applications, and the way these applications are structured is they run millions of steps of compute, communicate, compute, communicate. This runs over for millions of times. Okay. Each time a group of GPUs that work together computes some gradients. The next step, they all exchange the gradients. Once this exchange is complete, what they call as a collective, once it is complete, they go to the next iteration of it. Millions of such iterations happen. Now, let us say during this communication step, a GPU loses one of its packets. Now, what happens is till that packet is retransported back to this GPU, all the other GPUs participating in this communication in the collective are waiting till this communication completes. So, you have GPUs are the most precious things in this backend network, more precious than maybe our ASICs and switches, and these GPUs are stalled when a packet drop happens until the packet gets retransmitted. I think this is what Chintan was also stressing yesterday. So, we all see packet drops are a problem. And what are the common reasons for packet drops? Some of the common reasons for packet drops are like what Milind was talking in the morning, Alistair was talking in the morning about packets getting corrupted. The second case is we running out of buffers, buffer drops happening. And traditionally what would happen if not of this enhancement that we are talking about, if these enhancements are not there, what would happen? We wait for the end servers to recover. End servers could be either the transport protocol terminating at both the endpoints or even higher layer application layers. Right? They need a way to detect a packet has been lost and then retransmit all the way from the original sender back to the receiver. This is multiple hops, this takes multiple hops, and if the load on the network is already high, this makes it even more worse. If instead the lost packets can be recovered between the link partners, then we reduce the number of hops that are involved. With the standard 2-tier network, we reduce by 3x, and this reduction improves as the networks grow more deeper. So that was why we need link layer reliability mechanisms to address common reasons of packet losses, like packet getting corrupted or packet getting dropped due to buffer overflows. Now, there are two techniques that are being added in UEC. One was link layer retry and the other one was CBFC. Let us look at link layer retry first. Today Milind was talking about in the morning as well. As the link speeds increase, even small minor errors can result in packets getting corrupted, and we cannot even recover using FEC. Because the number of errors increase as the link rates increase. When they go more than 100 gig or 400 gig links, these errors are higher. Uncorrectable errors are higher. We can detect the errors, but we cannot recover the frames. And link layer retry is a mechanism where within the link partners, these corrupted packets are recovered instead of going back to the sender. So this uses the mechanism which involves the sender adding a sequence number in the frames that are being transmitted, as well as the sender also stores these frames in a replay buffer until it gets an acknowledgement from the receiver. And the receiver periodically acknowledges. It does not send every acknowledgement for every frame, but periodically it acknowledges the packets received, frames received, and then the replay buffer is released. And in case a frame is getting dropped, they follow the standard go back n mechanism, where all the n packets in the replay buffer after the error packets are replayed. Just a visual quick high level overview of how LLR works. In the normal case, let us say the frames 1, 2, 3 are being sent from the sender to the receiver. In the case of LLR, in the existing Ethernet preamble of the frames, the sequence numbers are encoded. Not just that, the sender also stores them in the replay buffer. Now, when these frames are received by the receiver, and receiver makes sure they are all expected packets, they are not corrupted, the receiver sends a periodic acknowledgement back to the sender. So this is not like an acknowledgement per frame, but it is periodic based on a user configured time. Periodically it sends what was the last successfully received frame number. And these are not regular Ethernet frames. These are sent via control order sets. These are 8-byte special control sequences that are inserted by the PCS layer when there are idle within the interframe gap or during idle cycles. These special messages are sent back. So this does not cause any bandwidth overhead. And once this periodic acknowledgement is received by the sender will release the buffers of whatever is stored in these frames that are stored in the replay buffer will be released. This is the normal operation of link level retry. Now let us see what happens in the case of packet corruption. Let us say frame 2 got corrupted. So now what happens is, when these frames are received by the receiver finds that using FEC or CRC, it finds that some frame is corrupted. So what the receiver would do, the receiver would drop the corrupted frame and all the subsequent frames, and the receiver would send a negative acknowledgement. This negative acknowledgement will have the sequence number of the last frame that the receiver successfully received. And now when this sequence NAC is received by the sender will use its replay buffer to send all the other frames with sequence number greater than this NAC sequence number. So this was an overview of how LR works. I will hand over to Jnanapriya to continue how.
Yeah. Is this customizable? The receiver you are sending like up to 3, up to 5, up to 10?
It's all configured. You can give a target spacing, saying within how much interval you should be sending the period.
Have you guys done the study? I mean, I don't know if anybody has done the study, what should be the magic number?
So this magic number depends on a couple of things. How many frames you send, and how much will be the size of a replay buffer, and the rate at which you send, and the link. It's a matter of how much is the link length, how much is the replay.
But have we done a study on the NAC? Like what should be the magic number? Like what kind of NAC is coming after how many packets? I can understand it depending on the environment and the cable and other things. This can change. But have we done the study? Like what is happening? Like how big, how small? You understand?
That numbers I have.
It's a 20-bit sequence number actually. In the preamble of the packet, a 20-bit is dedicated for sequence numbering. So maximum the sequence number starts from 1 to the maximum of 20 bits. That should be the maximum by the standard in the preamble. Once it reaches that limit, it would restart that.
So my question was a little bit different actually.
It's not that. The question is, we know that periodically that NAC should be sent.
Yes.
How do you define at what rate?
After what period you will
That
send
is
the
based
NAC?
on the speed and the
Some study.
cable length.
Okay.
Yeah.
RTT, basically the speed, cable length, round trip time, all were considered.
Still it is a magic number, am I right? I can send after 5, 10, 30, 40, whatever. Some study, some research has been done with the data.
There has been a lot of discussion that's during this way it was defined, right? Especially it's not just this, it has an implication along with your PFC. For example, you're configuring it with PFC. When this replay is happening, for example, you let the replay buffer grow big.
Then exactly. Okay.
Your PFC headroom should be enough to accommodate all this. So I think this is a more detailed question, a good question.
Yeah. So now let's talk about how do we bring LLR into SONiC. With SONiC's modular architecture, we are integrating LLR into SONiC, and it is built with 3 key components. It starts with LLR manager daemon, LLR orchestration, and configuration and management support. Let's deep dive into one by one component in detail. The first comes the LLR manager daemon. This is a new manager daemon running inside the SWSS Docker, and it's designed with 2 key considerations. The first consideration is that it accounts the vendor's replay buffer size capability based on the port speed and the cable length. And the second consideration is that to provide a simplified management interface. And the role of this manager daemon is to generate the LLR buffer profile whenever the feature is enabled on a port level. How do we do that? For that, we are introducing the vendor specific LLR INI file in the hardware queue, and it holds information like the replay buffer size capability, and it all tuned based on the vendors according to their capability. And the manager daemon parses this file and generates the lookup table. Once the feature is enabled by the configuration DB, manager DB parses this configuration information, uses the lookup table generated based on the INI file, and also refers the operational speed and the cable length to generate the LLR buffer profile needed for LLR mechanism. Once the profiles are generated, it pushes the configuration into the config DB for allowing any further modification possible by the operator. And also it pushes the